So in lesson 2, we will be looking at the absorption of radiation, and we are looking at the Beers-Lambert Law. In this class, we look at the instrumentation. We'll also look at the law itself, its assumptions, and its limitations. We'll also look at how we come up with calibration curves that are going to help us in quantitative analysis. And we'll also look at practical examples on application of the Beers-Lambert Law. Instrumentation. For us to be able to use electromagnetic radiation in quantitative analysis, of course, we need a spectrophotometer. Now, the spectrophotometer is a laboratory equipment, has 4 major components. We have the source of radiation that will be fitted in this compartment. We have the monochromator, again here. We have the sample compartment where you put your solution in a cuvette. You put it in here. And then you have the detector, and the detector is going to detect, or in other words, it's the eye of the instrument that will be able to look and see what has been absorbed out of what has been transmitted. And then, of course, you need a computer readout for you to be able to visualize the spectrum. The radiation source, as we said earlier, will need a source that is stable. It's not going to fluctuate in terms of the analysis, and it is going to cover the whole region of the analysis. You will also need a wavelength selector. Now, the purpose of the wavelength selector, remember, when radiation is coming from a radiation source, it is not going to be that the radiation source will only give you one wavelength that you need for the analysis. It is going to give you several. And so what the monochromator does, or the wavelength selector, which can be a filter or a monochromator, it is going to isolate a restricted region of what is coming from the radiation source. And then that restricted, isolated region is what is going to be sent to your sample container, and then you will be able to determine the absorbance from that. Then you also need a detector. Remember, everything that is happening in the form of radiant energy. It is light, it is radiation. But we need a gadget that is now going to convert this radiant energy into an electrical signal that is going to be plotted on a chart, and you are going to see in the form of a spectrum. Again, you need a signal processor, which is going to display the results digitally. And if you look at the schematic diagram of a spectrophotometer, we see all the components. You see the source of radiation. It's going to be allowed to enter into the wavelength selector through a slit. We have the monochromator. In this case, we are using a prism. Remember, we said you can also use a diffraction grating. The prism is going to disperse radiation into different wavelengths. Only the wavelength that you have instructed the equipment to select, the one that you need for analysis, is going to be allowed to pass through your sample cuvette as incident radiation. Maybe some of it will be absorbed. Whatever is going to be transmitted, and the detector now will determine the ratio of what is transmitted over what was incident, and you are able to calculate absorbance. And then from there you have the signal processor that is going to display the signal. For radiation sources, we defined radiation sources into 2 broad categories. We said we have continuum sources. Continuum sources will give you all the wavelengths. And then we have line sources. Line sources will only give you discrete lines. For example, examples of line sources, we have the hollow cathode lamp, the electrodeless discharge lamps. These 2 are used in atomic absorption spectroscopy and atomic absorption spectroscopy. We have lasers. Lasers are quite energetic, so we use them for fluorescence spectroscopy. We have, in the UV region, you can use a deuterium lamp, you can also use an argon lamp, and you can also use a xenon lamp. If you want a radiation source in the visible region, we have the tungsten. Again, just to remind ourselves of the output of a line source, discrete lines, the output of a continuum source, you get a broad spectrum. And now looking at the output of a deuterium and a tungsten lamp, the deuterium is going to give you output in the UV region. The tungsten is going to give you output in the visible region. And every time you have a spectrophotometer, the spectrophotometer will be fitted with these two lamps because you are using it in the UV region, such that you are able to do analysis in the whole region of around 200 to around 800 in the UV region. And what happens, by the time the deuterium lamp is no longer now giving you maximum intensity, the tungsten lamp picks up and starts giving you some energy in the visible region. So the importance of the two lamps in UV region. We've also looked at the interaction of electromagnetic radiation with matter. We said it can involve things like reflection, especially at the surfaces. Remember, we are using glass cuvettes. So when light comes in through the surface, some of it will be reflected, some of it will be allowed to go through. Whatever is allowed to go through will be, some of it will be scattered. Again, as the light is coming out of the cuvette on the other side, some of it will be refracted, bedding of radiation, and some of it will be transmitted. And our interest now is to measure how much was absorbed so that we can use it for quantitative analysis. And for us to be able to use this in quantitative analysis, there are two laws that were derived sometimes back, one by Lambert, the other one by Beer. And the one by Lambert relates absorbance, which is what we are defining as the logarithm of what is incident. PO is the incident radiation, whatever is coming from your, of course, from your lamp through the wavelength selector onto the sample. That's what we are calling PO. Then we have P is what is transmitted. After it comes into your sample, some of it is absorbed. What is transmitted or what goes to the detector to be detected. And we are saying that this absorbance is equal to K, a proportionality constant, or in other words, we are saying the absorbance is going to be proportional to B, and B is the path length of the cuvette, the distance that light is going to traverse through as it interacts with your sample before it comes out from the other end. Then Beer also related absorbance, but in this time he related it now to concentration, such that now we have absorbance is directly proportional to the concentration. Again, K is a proportionality constant. And so now from the two laws we have the Beer-Lambert law, and the Beer-Lambert law relates absorbance to both concentration and the path length. Again, in this case, we are using A as the proportionality constant, which is absorptivity. So the Beer-Lambert law is a linear relationship between absorbance and concentration. And you can now see the importance of this law because it helps us to quantify. You are able to say how much in terms of concentration is in a certain solution. Now, Beer-Lambert law permits chemists to measure the concentration of a solute in a solution by measuring the absorption of radiation. Now, the Beer-Lambert law is expressed as A for absorbance is equal to small a, where A is absorptivity, B is the path length, and C is the concentration, which is also equivalent to the molar absorptivity, epsilon, the path length, B, and the concentration, C. And as you can see, we can actually plot absorbance against concentration for a set of standards, and you get a linear relationship with an equation of the line in the form of the equation of a line y is equals to mx plus c. M is the slope, Of course, X is the concentration of the standard that you are plotting, and C is the intercept. Now, the slope of this Beers-Lambert plot is going to be equal to, because we are plotting absorbance against concentration, the slope then can only be AB, absorptivity times the path length, or can be equal to the molar absorptivity times the path length. We will define the difference between absorptivity and molar absorptivity shortly. We also have transmittance. Now, transmittance is the fraction of light that is going to the detector, meaning the fraction of light or the light that is not absorbed. And this is what happens. We have the light that is being incident on the cuvette. Remember, the cuvette contains the solution that you want to absorb or to measure the concentration. After absorption, whatever is going to come from the other end, in other words, the transmitted radiation, is going to be attenuated in energy. You can actually see the arrow looks thinner. This one is a bit thick, meaning some of the radiation has already been absorbed by the solution. And so now we define absorbance as the negative logarithm of P, the transmitted radiation, over P naught, the incident radiation. And we are saying that T, which is transmittance, is the fraction of light that reaches the detector after passing through the sample. In other words, T is going to be equal to P, the transmitted radiation, over P naught, the incident radiation. And again, absorbance is the negative logarithm of transmittance. So what does this mean in terms of the Beers-Lambert law? It means for lower concentration, in case your sample has low concentration, then you don't expect the absorbance to be high. And that's what we are saying here. Low concentration, lower absorption. If you have higher concentration, then the solution is going to absorb more radiation because you have more molecules that are absorbing radiation. So we are saying absorbance is directly proportional to the concentration. What is the relationship between absorbance and the path length? We can use L or B. So this is the same as B, the path length. Now in this case we are saying, again, there is going to be a direct relationship. Notice that on my right side, the path length is short. On this side, the path length is longer. Now what this means, it means if this light is coming in at this point, it is going to have a shorter distance as it traverses through the sample solution, as compared to this side, whereby as the light is coming in, it has a longer distance to traverse. So it is going to interact with the molecules more, and it is going to be absorbed more. So again, we have absorbance directly proportional to path length. So let's now try to differentiate between absorptivity and molar absorptivity. Whatever we are calling absorptivity is epsilon, and absorptivity is A. Sometimes people can use alpha. Now, when we use concentration and we express it in form of molar concentration in moles per liter, then the proportionality constant we use is the molar absorptivity. So then we can express the Beers-Lambert law as A is equals to the molar absorptivity multiplied by the path length and then multiplied by the concentration. And we refer to the epsilon as molar absorptivity. So what are the units of molar absorptivity? Again, we know that absorbance is equal to molar absorptivity times B times C. So if we make molar absorptivity the subject, then we find that the molar absorptivity is basically absorption per unit concentration, because it is going to be A over BC. And absorbance is unitless. Path length is usually 1 centimeter. And of course, the units of concentration are moles per liter. And that means the units for molar absorptivity are going to be liter per mole per centimeter. What about absorptivity? Now, when concentration is expressed in grams per liter, not in moles per liter, we use absorptivity, A. And so now again, A is going to be equal to absorbance divided by the path length, which is 1 centimeter, divided by concentration in grams per milliliter. And so now the units of absorptivity will be liters per gram per centimeter. And so now we are able to differentiate between molar absorptivity and absorptivity. By looking at the units given, you are able to know whether to use alpha or A or whether to use epsilon. So what happens when you are doing analysis? You have the sample, you have the source of radiation. The source of radiation comes through the sample, and this sample can be anything. You might be wanting probably to determine the amount of glucose in somebody's serum or somebody's urine. And then it is going to go to the detector, and the detector is going to measure absorbance. Remember, absorbance is the negative logarithm of transmittance, and transmittance is a fraction of light transmitted to the light that is incident, P over P naught. And we summarize the different units. Absorbance has no units, that's why we have a dash. The molar absorptivity has units of liter per mole per centimeter. B, the path length, has units of centimeter, and usually it is going to be 1 centimeter unless otherwise specified. If it is not 1 centimeter, it's always going to be specified. And then we have C, the concentration, which is in moles per liter when we are using molar absorptivity. When we are using absorptivity, then it is going to be grams per liter. Now, the Beers-Lambert law is a very important, it's a very simple expression, but yet very highly useful in terms of quantitative analysis. For example, assume somebody was to ask you to prepare, or somebody was to ask you to give the concentration or to measure the concentration of an unknown sample. Let us assume in this case somebody has given you some blood serum belonging to a patient, and they want you to determine the amount of iron in the sample. How do you go about this kind of an analysis? You know that you want to determine iron in a solution whose concentration you don't know. We can use the Beers-Lambert law. How do we go ahead and use this? We make what we call standard solution. Now, a standard solution is a solution whose concentration is known. And the solution concentration is known by the analyst, because you are going to make these solutions by using a standard of iron. And you make them in increasing concentration. Start with the lowest concentration and you increase the concentration. For example, let's take an example. We can start with 2 ppm, 4 ppm, 6 ppm, 8 parts per million, 10 parts per million, maybe 12 parts per million. Then you have the unknown, and this is the solution whose concentration you don't know. Then you measure the absorbances of the standard solutions. Remember, these are solutions that you prepared and whose concentrations you know. You measure the absorbances, and before you measure the absorbances, if you didn't know the lambda max is the wavelength of maximum absorption for iron, the first step would be for you to determine the wavelength at which iron is going to absorb, so that once you determine the wavelength of maximum absorption, then you can analyze the standards at the same wavelength. And you can also analyze the unknown at the same wavelength. In this case, again, we would select lambda 2 because lambda 2 is the one that is giving you the maximum absorbance or the highest absorbance. Remember, we made the standards, and then we analyzed the standards by the use of the lambda max that we already determined if we didn't know. And then after that, you plot the absorbance of the standards against the concentration of the standards. And you obtain the linear relationship between absorbance and concentration as per the Beer-Lambert Law. And we said the line is going to be in the form of y is equals to mx plus c. We already defined the slope is going to be equal to the molar absorptivity times the path length, or the absorptivity times the path length. Then, once you've already determined the absorbance and the concentration, and you've already prepared the calibration curve, you then measure the absorbance of the unknown sample. Now, if the absorbance of the unknown sample does not lie within the calibration curve, then you need to dilute your sample. If the unknown sample lies, absorbance lies within the concentration, the calibration curve, then we are safe. Then we can use interpolation to determine the concentration of the unknown sample. That is if you are drawing the graph by hand. However, if it is computer generated, the computer will always, you can always get on the thread line, you can always get the equation of the line, which can be rearranged to get x. Remember, x is the concentration of the unknown. Y is the absorbance of the unknown sample that you've also measured. And you are now able to determine the concentration of the unknown sample, which again we said is the amount of iron in somebody's serum. Now, there is also what we call correcting for background absorbance. And background absorbance is any absorbance that is not coming from your sample. It might be coming from maybe your solvent or maybe from the cuvette. And the way you do it, you first of all determine the absorbance of everything. That is the absorbance of the cuvette, the absorbance of the solvent that you are using to dissolve the sample, and the absorbance of the sample. And this, you get the value that we call absorbance for everything, or absorbance all. Then you exclude the sample, meaning you only measure now the absorbance of the cuvette and the absorbance of the solvent. And here now you get the absorbance of the blank. If you subtract the two, then that will give you the corrected absorbance that is resulting from the sample, and we are good. So it's always important for us to measure or to do the background absorbance correction so that you can always correct for any background absorbance that you are not likely to account for. We've already seen that we are using absorbance and concentration. Why are we not using transmittance? Because transmittance and concentration are not directly proportional. And we can see this by looking at the relationship between transmittance, the path length, and the concentration. If you look at transmittance and path length, you can see the relationship is not linear. Transmittance and concentration, again, the relationship is not linear. And therefore, we usually measure absorbance and not transmittance. So let's look at an example of how you are able to calculate transmittance from absorbance. And we have been given a percentage transmittance of 92.1, and we are required to calculate the absorbance. And already we know that absorbance is the negative logarithm of transmittance. So 92.1 translates to a transmittance of 0.921, and you just need to get the negative logarithm of it, and you record that as the absorbance. Similarly, we can be able to calculate absorbance from transmittance. So in this case, you are given a transmittance of 0.375. Now, I'm sorry. In this case, you have been given absorbance, and you are supposed to calculate percent transmittance. So the question here should be given the following absorbance data, calculate the transmittance. So in this case, you are given an absorbance of 0.375, and you are required to calculate transmittance. So transmittance is going to be equal to the 10 to the power of minus absorbance because of the relationship between absorbance and transmittance. And once that is done, you get the transmittance as 0.42, which in terms of percentage, we multiply by 100 to get 42%. Now, as we have seen, the Beers-Lambert law is a very simple expression, but before this expression came into being, there are several assumptions that had to be made. And so now we look at the different assumptions that had to be made. Now, the first assumption was that interaction that is responsible for attenuation of the incident radiation is absorbance. There is nothing else that is absorbing apart from the analyte that you are interested in. And so we are saying that the law will break if reflection and scattering are not compensated for. So we have to compensate for reflection and scattering, and it can also break if the radiation is being re-emitted in the form of fluorescence. And this becomes a problem if there is stray radiation again in the instrument. The second assumption, we assume that the absorption is only measured at a single wavelength. In the absence of measuring absorption at a single wavelength, then the law is going to break, such that you get a negative deviation, which is a decrease in absorbance than what you should actually record when you do the analysis. In this case, we find the absorbance against wavelength, and we are saying you can either determine absorbance at this point, band A, or you can determine it at band B or band A. Now, the problem of determining your absorbance at band A, at band B, is you can see as the wavelength here is changing, the absorbance here is also changing, it's increasing. At this point, as the wavelength is changing, the absorbance is relatively remaining the same. And so, it's always important, that's why we determine the absorbance at lambda max, because at lambda max, the absorbance is not changing significantly as we change the wavelength. Then we also assume that the path length is the same over the volume being measured. The path length should not change. And it is for that reason we don't have circular cuvettes. All cuvettes are triangular, because when you have a circular cuvette, as you can see, the distance that light is going to pass through may not necessarily be the same. For example, at this point, if you look at the value of B and you look at the value of B at this point the light is traversing a larger distance than at this point. Again, because of the relationship, that will translate to a problem, and you are likely to encounter deviations to linearity. We also assume that the nature of the absorber does not change. The absorber remains the same. In this case, there is not going to be any reaction. There is not going to be any dimerization that is going to change the nature of the absorbance so that its absorbance will remain the same. What happens when these assumptions don't hold? When these assumptions don't hold, then we have deviation from linearity. The Beers-Lambert law is no longer linear. You'll notice some deviations. The deviations can either be positive, meaning the absorbance increases, or the deviations can be negative, meaning the absorbance is decreasing, and these deviations are deviations from the ideal situation being adherence to linearity. Now, the deviations to the Beers-Lambert law can be divided into three major categories. We have the real deviations, and these limitations, as a way the law was derived, this law only works well for dilute solutions. If your solutions are not dilute, then we start getting interactions with the solvents and other solute molecules, or you can even get things like hydrogen bonding, and these are likely to affect the absorbance measurement. Or if the concentration is so high, some molecules will screen others from actually receiving the radiation, and again this will interfere with the resulting absorbance measurement. We said for this law to be derived, the absorber should not change, meaning the absorber should not change in terms of the ability to absorb radiation. So when you have acid-base chemistry, for example, like we have in the form of indicators, then that acid-base chemistry changes the nature of the absorbing molecule. And so in that case, for example, you can see at pH greater than 4.4, this molecule is absorbing and emitting, and the color that you observe is orange. At a pH less than 3.2, when this molecule has gained a proton, then you can see the molecule now is red in color, because now the nature of the absorber has changed. And this again will translate to deviations onto the linearity of Beers-Lambert law. We also have instrumental deviations as the other category. Now, instrumental deviations can be again classified as either mismatched cells and cuvettes, polychromatic radiation, and stray radiation. Mismatched cells and cuvettes, meaning the cuvette, the way you are handling the cuvette changes, and this can result from the imperfection in the characteristics of the glass that is making the cuvette. We also have polychromatic radiation. Again, we say this law works best when we have monochromatic radiation. Monochromatic radiation, light of a single wavelength. And again, you can see with the polychromatic radiation, you are getting a negative deviation to the Beers-Lambert law. Another issue is stray radiation. Now, stray radiation is any radiation that is coming from any other source, and it is not passing through from the source of radiation to the wavelength selection. It might come from maybe improperly closed instruments, reflection from the lenses of the spectrophotometer, and so on and so forth. Again, polychromatic radiation leads to a negative deviation of the Beers-Lambert law. And when we have stray radiation, we have to add the component of stray radiation to the measurement of transmittance. Remember, we said the transmittance is P over P naught, but when there is the presence of stray radiation, we have to add the component of stray radiation, which is P subscript S, S for stray radiation. And you can see this becomes a problem at high concentration. As the concentration becomes high, stray radiation becomes much of a problem. The deviation is quite significant and quite announced. As we can see, without any stray radiation, adherence to linearity, with some stray radiation, only 0.2 stray radiation, some deviation, and by the time the stray radiation is 5%, there is quite high deviation on from linearity. Now we have looked at the Beers-Lambert law and how we can use it for quantitative analysis. Perhaps now we should look at some practical examples for us to be able to understand the concept and the importance of the Beers-Lambert law. And we start by looking at an example where some students in a class of spectroscopy made or prepared a calibration curve, and they collected absorbance data at a wavelength of 520. And to analyze an unknown solution that was provided to the students took an ml of the unknown and diluted it to 100 milliliters. Remember, dilution is important to ensure that the absorbance of the unknown, because it might be very highly concentrated, is going to fall within the calibration curve. And every time, it's always a good practice to think of dilution, because you get samples that are concentrated, samples that are undiluted, and it is your, it's your responsibility as the analyst to think of dilution. Then when they made the calibration curve, they determined the absorbance of the diluted unknown, and it was determined to be 0.365. So we see the calibration curve that was made, absorbance against concentration. And you can see the line is linear. The computer has already generated the equation of the trend line. So in this case, we don't have to interpolate manually because it is a line generated by the computer. And we can answer the first question. By the use of this calibration curve, we need to determine the concentration of the diluted unknown sample. Remember from the previous slide, we have seen that the unknown had an absorbance of 0.365. If we didn't have the equation of the line, then we would come and look at the y-axis and determine 0.365, and then we would interpolate and read the concentration. However, in this case, because the equation of the line is given, we only need to make x our subject because we already know y. And that's what we are doing here. X is going to be equal to y, which is the 0.365 plus 0.0032, which is the intercept from the trend line. You divide that by the slope, the 160.4, and you get the concentration as 0.023 molar. How we know the concentration is going to be in units of molarity is because the concentration here that is plotted on the graph and that's actually provided is going to be in molarity. The second part of the question requires you now this is the concentration of the diluted unknown. Remember, the students took 1 ml, they diluted it to a 100. So what is the concentration of the undiluted? If you are an analyst in a lab, you will not be reporting the concentration of the sample you diluted. You'll be reporting the concentration of the sample that was given to you, the original sample without dilution. So the solution was diluted as follows. 1 ml of the unknown stock, because it is a solution whose concentration you didn't know, was diluted to a total volume of 100 milliliters. This means 100 times dilution. And therefore, if we want to get the original concentration, we need to multiply the concentration obtained from the previous section, which is 0.023. If you multiply this concentration by 100, then you get the concentration of the original sample, which is 0.23 molar. The third part of the question requires you to calculate the molar absorptivity, or to report the molar absorptivity coefficient epsilon of the food color. Again, this is doable because if we look at the calibration curve, it has the form of y is equals to mx plus c. C is the intercept and m is the slope. And here we know that m is 160.4. By definition, the slope is the product of the molar absorptivity times the path length. And therefore, we can make the molar absorptivity the subject of the formula, and we can be able to determine that by taking the slope, dividing it by the path length. The slope is going to be 160.4 per molar. And this is important because you see, when you get the equation of the line, it is not giving you the units. But because we know the gradient or the slope is determined by the change in y, unitless, change in x has units of molarity. So the gradient or the slope is going to have the units of per molar. Then we divide this by the value of b, and in this case, b is 1 centimeter. You divide that and you get the slope as 160.4 per molar per centimeter. Now we also have a second example that is also worked for us. And in this case, a medical technologist in a hospital is using ultraviolet visible radiation spectroscopy to determine iron in a patient's blood. And of course, it is difficult calorimetrically to determine iron, so you complex it with another reagent. And when this is done, he obtains the following data. And in this case, you are told to note that concentration is in micrograms per deciliter. So we have the concentration and we have the absorbance. Again, notice that we have the absorbance of the unknown sample, which is sample number 555 from the patient. And the question requires us to prepare a Beers-Lambert law, or in other words, a calibration curve. And then from the plot, we can determine the concentration of iron in the patient's blood, serum. And then you are given the normal serum concentration of iron to be 40 to 155 micrograms per deciliter. And then the question is requiring you to think of the advice the patient is likely to be given by the medical doctor based on how much iron is determined from his or her blood sample. So we go ahead and do a computer-generated plot. We have absorbance against concentration, and we have the trend line. The equation of the line is y 0.062x minus 0.0135. And you can see what we've tried to do. We've just tried to take the absorbance of the patient, assuming we didn't have the equation of the trend line, and we are trying to interpolate the graph to get the concentration of the patient, and we can see the concentration is going to lie around here. But now, because we have the equation of the line, we can just use the computer-generated equation to solve for x. And because we know y to be 1.17, we can solve for x, and we determine the concentration to be 190.9. And that is now the concentration of iron in the patient's blood. And because we were not given any information regarding dilution, we assume the sample had already been analyzed the way it was. And so now we have found the concentration to be 190. And you realize the normal concentration of iron is between 40 and 155 micrograms per deciliter, meaning this patient's sample or iron is far much beyond what is normal. And so you'd expect the patient to have a discussion with the doctor on maybe medication or remedies to correct for that high iron levels. And so, class, I'm glad to summarize what we have done this today on the 2 lessons. From the first lesson, part 1, we've already looked at electromagnetic radiation. We've seen electromagnetic radiation behaves as a wave or a particle. Behaves as a wave, can undergo interference, can undergo diffraction. Behaves as a particle, a packet of energy, can be absorbed or emitted. We have also seen that absorption of light in ultraviolet visible involve valence electrons. Now remember, the valence electrons are the outermost electrons, and these electrons can always absorb energy, and they can be promoted from lower energy levels to higher energy levels. When they are excited to higher energy levels, they can relax back to the ground state, and in so doing, they can emit energy. We've also seen that electromagnetic radiation is again absorbed in quantas of energy. Energy is not just absorbed anyhow. It has to be energy that matches the energy difference between 2 energy states. And we said, imagining yourself climbing a ladder that has steps, you can only go from one step to the other step. You cannot stop in between. That's exactly what we are calling quantization. An electron cannot stop in between the energy levels. It has to go from the lower energy level to a higher energy level. We've also seen that electromagnetic radiation can be used for both qualitative and quantitative analysis. Qualitative analysis, you are able to say maybe a certain metal is present or a certain metal is absent. Quantitative analysis, you are able to say how much of a certain metal is present, by the use of quantitative analysis, as we saw in the Beers-Lambert determination. Now, we also saw in the chemistry of vision, the color that you will always observe is a color that is a complement of what is absorbed. And we've looked at different examples. We looked at chlorophyll. We looked at a pigment such as beta-carotene. We looked at a pigment such as lycopene. For part 2, we also saw the absorption of radiation follows the Beers-Lambert law. And the Beers-Lambert law relates absorbance to concentration through molar absorptivity and the absorptivity. And we also saw that the path length is a constant, because usually path lengths don't change unless otherwise stipulated. We said unless otherwise stipulated, you should always take the path length to be 1 centimeter. However, maybe you may get some other instances whereby the path length may not be necessarily the 1 centimeter, but in that case, the path length will always be specified. Now, we also saw that you only use the molar absorptivity if the concentration is expressed in moles per liter or molality. Otherwise, if the concentration is expressed in grams per liter, then in this case, we use absorptivity. And we saw there is a linear relationship between absorbance and concentration, and there is a logarithmic relationship between absorbance and transmittance. For that reason, we usually measure absorbance and not transmittance. We also saw a calibration curve generated using a standard, which we are calling the calibration curve, is helpful to estimate the concentration of a known sample. Meaning, if somebody was to give you like a sample from a well and they tell you to determine how much iron or how much magnesium is present or even calcium, we can always do this by generating a calibration curve. You get standards of whatever metal you are trying to determine, different standards of different concentration, and then you measure the absorbance. You plot absorbance against concentration, and then you make sure that the absorbance of the unknown, once you do the measurement, is always going to fall within the absorbance of the generated calibration curve. If this does not happen, as an analyst, it's now your opportunity to think about diluting the sample to always bring it to the absorbance level that you want it to be at. You can always know by how much you will dilute the sample, because of course you can see the absorbance that you have measured and you can see the absorbance range of your calibration curve. We also saw that Beer's law works best for dilute solutions, and these are solutions that are less than 0.001 moles per liter. So if you don't make solutions within this range, you are not likely to generate a linear curve, or the curve is likely to deviate from linearity. So always keep in mind that you need quite dilute solutions for you to be able to use the Beers-Lambert law for analysis. And so class, I want to end the lesson at this point, and I want to thank you and request you to keep safe. Thank you so much, and thank you for listening.
We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.